Imagine you're standing on a foggy hillside. You can't see the valley floor. The mist hides everything more than a step away. But you can feel the ground tilt beneath your boots. Which way is downhill? You take one small step that way, then feel again, and step again. Slowly, blindly, you walk to the bottom. This is exactly how a machine learns. A model has knobs, its parameters, which we call theta, and a loss, j of theta, that measures how wrong it is. Most models are far too tangled to solve in one clean formula. So instead of solving, we descend. We start somewhere, feel the slope of the loss, and step downhill towards smaller and smaller error. That method is gradient descent, the single engine behind almost every model you'll ever train. Let's build it from the ground up, first on a simple curve, then on a full landscape. Strip it down to one parameter, so we can draw the whole thing. Here is a loss curve. The horizontal axis is the parameter theta. The vertical axis is how wrong the model is. This particular valley is a smooth ball with its lowest point at theta equals 3. Our goal is that bottom, the smallest possible loss. But the model can't see it. All it has, at wherever it currently sits, is the slope of the curve right there, the derivative j prime of theta. Say the model sits here, to the left of the bottom. The tangent line leans downhill to the right. Its slope is negative, and a negative slope carries a simple instruction to go lower, move to the right, toward larger theta. On the other side, it's the mirror image. To the right of the bottom, the curve tilts up to the right. The slope is positive, so the way down is to the left. The rule is always the same. Step in the direction opposite to the slope. Downhill is minus the derivative. Here is the rule that does all the work. New theta equals old theta, minus alpha times the slope. The minus sign points us downhill. And alpha, a small positive number called the learning rate, decides how big each step is. Let's put real numbers through it. Take the loss theta minus 3, all squared. So its slope is 2 times theta minus 3. We start at theta equals 0, with a learning rate of 1/10. The true minimum is at 3, so we'd like our steps to march us rightward toward it. First step. The slope at 0 is 2 times minus 3, which is minus 6. So new theta is 0 minus 1/10 of minus 6. That's 0 plus 0.6, giving theta 1 equals 0.6. The negative slope pushed us right, exactly as promised. Second step, from 0.6. The slope is now 2 times minus 2.4, minus 4.8. 1/10 of that is minus 0.48, and subtracting a negative adds. So theta 2 is 1.08. Notice the step got smaller because the slope is gentler nearer the bottom. One more, and theta 3 is 1.464. Each step shrinks as the ground flattens, and the values creep steadily toward 3. That's convergence, the descent easing gently into the minimum. Watch the whole descent at once. The dot starts up on the left wall, and each gradient step drops it a little further down and to the right. Big strides where the slope is steep. Tiny shuffles as it settles into the basin at 3. Now for the real thing, in 3 dimensions. A model rarely has one parameter. Give it to theta naught and theta 1, and the loss becomes a height above the plane, a whole landscape. For a simple squared loss, that landscape is a ball, and the lowest point of the ball is the best the model can do. Down at the bottom sits the minimum, right where both parameters are perfect. Our job is to roll a ball from some random starting point all the way down to it, using nothing but the local slope. In 2 dimensions, the slope has a name and a shape. The gradient, written with an upside-down triangle. It's the vector of partial derivatives, how the loss changes as you nudge each parameter, and it points in the direction of steepest ascent. Steepest way up. So to go down, we simply flip it around and follow its negative. So here is gradient descent on the ball. From high on the rim, the ball takes a discrete step straight down the negative gradient. Then it feels the new slope and steps again. Watch each arrow point downhill, and the steps shrink as the surface levels out until the ball settles at the very bottom. In full, then, this is the whole algorithm on one line. The parameter vector theta gets replaced by itself minus the learning rate alpha times the gradient of the loss at theta. The same rule you saw in one dimension, only now theta and the gradient are vectors. So every parameter updates together in a single move, and the gradient itself is just a stack, one partial derivative per parameter. Each entry answers the same little question. If I wiggle this one weight, which way does the loss go and how fast? Line them up, negate, scale by alpha, and you have the step for the entire model at once. Everything now hinges on one dial, alpha, the learning rate. It sets the length of every step, and getting it wrong ruins the descent in one of two opposite ways. Let's watch all three cases on the same curve. On the left, alpha is far too small, 200ths. Every step is a timid shuffle, and after 8 of them, the dot has barely left the wall. It will get there eventually, but it crawls. Slow, wasteful, sometimes hopelessly so. In the middle, alpha is just right, a tenth. The steps are bold where the wall is steep, then automatically gentle near the floor, and the dot glides smoothly into the minimum. This is the sweet spot every practitioner is hunting for. On the right, alpha is too large, bigger than 1. Now each step overshoots the bottom and lands higher up the far wall than it began. The dot ricochets from side to side, climbing away from the minimum instead of toward it. The loss explodes. This is divergence. And it's the classic way training blows up. Too small and you crawl. Too large and you diverge. Tuning the learning rate, often just trying a few and watching the loss, is one of the most important knobs in all of machine learning. One practical wrinkle. To compute the true gradient, you'd sum the error over every training example. And with millions of them, a single step becomes painfully expensive. So there's a family of choices for how much data to use per step. Batch gradient descent uses all the data every step. Its path is smooth and true, but each step is heavy. Stochastic descent, SGD, swings to the other extreme, using just one random example per step. It's fast and cheap, but the gradient is a noisy estimate, so the path jitters. Mini-batch splits the difference, a small handful at a time, and it's what almost everyone actually uses. Here's the difference you can see. Both methods head for the same bottom. Batch, in green, glides straight down. Stochastic, in pink, wobbles its way there, overshooting a little, backtracking a little, because each noisy step only roughly knows which way is down. Noisier, yet it still arrives, and far more cheaply. Now the deepest catch of all, and it's about the shape of the landscape. When the loss is convex, a single clean ball, gradient descent cannot lose. Wherever the ball starts, it slides to the one and only bottom. Every local minimum is the global minimum. But most real loss surfaces are not convex. They're bumpy, with many valleys. And gradient descent only ever knows the slope right where it stands. It can't see over a ridge. Start on the wrong side, and the ball rolls into a shallow local minimum and stops. Stuck, never reaching the deeper valley beyond. That's the price of a non-convex landscape. So convex problems are the safe, solvable ones, and they get a lesson all their own. For everything else, where you start and how you tune the descent, genuinely decide where you end up. Your turn, one clean step by hand. The loss is theta squared, so its slope is to theta. You start at theta equals 1, with a learning rate of 1/10. What is theta after a single gradient descent step? Pause, work it through, then let's compare. Here's the walkthrough. The slope at theta equals 1 is 2 times 1, which is 2. Plug into the rule. Nu theta is 1 minus a tenth of 2. A tenth of 2 is not zero point 0.2. So theta becomes 1 minus. That zero point 0.8 one step has nudged us from 1 toward the minimum at 0. If you got not zero point 0.8, you've truly got gradient descent. Trap 1. The sign. The gradient points uphill toward greater loss. You must subtract it, not add it. Flip that minus to a plus, and you climb the loss instead of descending. The model gets worse every step. Trap 2. The learning rate. Too large and the steps overshoot and blow up. Too small and you crawl forever. There's no universal value. You tune it and you watch the loss to know it's working. Trap 3. Gradient descent reliably reaches a local minimum, but that's the global best only when the surface is convex, a single ball. On a bumpy landscape, it can settle for a shallow valley and miss the deepest one. Trap 4. If your features live on wildly different scales, the ball stretches into a long, thin ravine and descent bounces across it, zigzagging instead of heading down. Scaling the inputs rounds the ball and lets it flow straight to the bottom. And trap 5. Descent is iterative. It approaches the minimum but never lands exactly on it. You stop when the improvement falls below a small tolerance, at good enough. Waiting for the gradient to hit exactly 0 is a wait that never ends. Let's lock it all in. One rule runs the whole show. Nu theta equals old theta, minus the learning rate times the gradient of the loss. The heart of it is the direction, minus the gradient, the steepest way downhill. Feel the slope. Step against it. Repeat. The learning rate sets the pace, and it's a balance. Too small, and you crawl. Too large, and you diverge. Tune it by watching the loss, and where you land depends on the terrain. Descent finds a local minimum for sure. The global one for free only when the loss is convex. Master this single step, and you understand the engine that trains nearly every model there is.